We've talked about Newton's first law, the law of inertia, the tendency of things to keep doing what they're doing, to maintain a constant state of motion. So things at rest tend to stay at rest unless there's an external force, and things in motion tend to continue moving at a straight line, in a straight line, with a constant velocity, unless acted on by an external force as well, or a net force, right? That was the other word that we used it. An unbalanced force would be called a net force. And that brings us to Newton's second law. Newton's second law was F net, or net force, equals mass times acceleration. And that means that the greater the force, the greater the acceleration will be, just judging by that formula. Or, the lower the mass you have, the less force you will need to achieve a certain acceleration. Okay, so the greater the mass, the lower the acceleration, the greater the force, the higher the acceleration. That's one way of looking at it. Newton's third law is the action-reaction law. So it says that for any force exerted, there is going to be an equal and opposite reaction force. And the easiest way to illustrate that is just pushing on a wall. Okay, a wall is extremely massive. So obviously, a wall is not usually just standing there on its own. It's attached to a building, which is attached to the ground. And so by pushing on a wall, you are pushing on an extremely massive object. Essentially, you're trying to push an entire building. And it's not going to move. It's way, way too heavy, right? But you are exerting a force on that building. And when you are exerting a force on that building, it is pushing back on you with exactly the same amount of force. And so, let's say that you would, I don't know, jump and drop kick a wall. So now you're in the air and you've kicked the wall. It's going to push you back, right? You're not going to be able to move the building because it's so massive. And so the building exerting a force on you is going to accelerate you in the opposite direction. That's Newton's third law. And that applies for anything. So if you serve a volleyball, the volleyball flies away from you because you exerted a force on it, but it actually exerted the exact same force on you. The question then comes, why don't I fly backwards every time I hit a volleyball or a golf ball or every time I think of anything? That's because your masses differ. So the mass of a volleyball is much, much less than your mass. And so, like Newton's second law says, the greater the mass, the smaller the acceleration will be with the same force. And so, though you are exerting a force on the volleyball and it is exerting the same force on you, the smaller mass of the volleyball means that it has a much greater acceleration. Okay? So, let's look at this example here. A car with a mass of 1,000 kilograms is driving down a road, and a mosquito with a mass of 0.0007 kilograms hits the windshield. The mosquito exerts a force of 2 newtons on the car. What is the acceleration of the mosquito? And what is the acceleration of the car due to the force of that impact? So Newton's third law says that the 2 Newton force that the mosquito exerted on the car is the same as the 2 Newton force that the car exerts on the mosquito. So we can use that in conjunction with Newton's second law, F net equals ma, to figure out what's the acceleration of each of those things. And often that's what you're going to see. Newton's third law, we're going to use it in conjunction with Newton's second law. So let's give this a shot here. F net equals ma. These are vectors. Mass is not a vector, and so I don't put a vector symbol on the top. So we know that the force being exerted on the car, let's start out with the car, is 2 newtons. And the mass of the car is 1,000 kilograms. So then we're trying to solve for the acceleration of the car. Now, I've said previously that most often I really like to rearrange the formula first and then put in the numbers. So that would mean getting acceleration by itself, but in this case, I want to illustrate a specific thing. Okay, so don't think that I'm breaking my own rule. It doesn't matter in this case. So I'm looking for the acceleration of the car, right? We're talking about the car in this case because we've put in the mass of the car. I also want to do the same thing for the mosquito. F net equals ma vector vector. 2 newtons is also acting on the mosquito. So the mosquito pushed on the car with 2 newtons, so the car is pushing on the mosquito with 2 newtons as well. And so the mass of the mosquito is 0.0007 kilograms, and we are solving for its acceleration. So this is the mosquito, and this over here is the car. And so now we can solve for the acceleration. That's just taking 1,000 and dividing it, right? So we're going to 2 divided by 1,000 is going to give us the acceleration that the mosquito is putting on the car. Okay, so 2 divided by 1,000 is the acceleration. So the acceleration of the car is going to be 0.002 meters per second squared. Meters per second squared. And then when we do the same thing for the mosquito, we get the acceleration of the mosquito is 2 newtons divided by 0.0007 kilograms, and that gives us an acceleration of 2,857 meters per second squared. Now remember, this is how the velocity is changing in a certain amount of time. And so what this says is that the car's velocity is going to change by 0.002 meters per second every second that the mosquito is pushing on the car. But the mosquito is only going to push on the car for a fraction of a second. And so in reality, the car's velocity isn't even going to change by 0.002 meters per second, which is imperceptible anyway for the person driving the car. It's going to change by even less than that, which is why you'd never notice a swarm of bugs hitting your vehicle. But the mosquito, its velocity is going to change by 2,857 meters per second every second. But again, because the impact is much less than a second, it's just a fraction of a second, the mosquito's velocity is going to change by much, much less than this. Okay, so they are both experiencing the same force, just in opposite directions, and that can tell us how their acceleration is going, or how their velocity is going to change in whatever the impact time is. Okay, now both of these are vectors, so they should have directions, but the question doesn't tell us anything about the direction things are happening in. Let's just say that the car is moving forward and the mosquito is moving backward. And so that means that the force exerted on the car will be backward compared to the car, and the force exerted on the mosquito will be forward. Okay, so the force or the acceleration they're going to experience is just the opposite of the direction that they were moving before. Okay, so backward, and this guy we're saying is forward. But again, both of them, from their own perspective, the force they're experiencing is going to be backward. They're just moving different directions. So here's a classic Newton's third law question, and maybe you've tried this with a friend before. What happens if you're both standing on ice? Maybe you're wearing skates, and you both push each other. So you put your hands together and you both push. What happens to you? Well, you both move backward, probably, and one of you, depending on who's heavier, may move backward faster than the other. Okay? And so you're both experiencing the same force, you're pushing against each other, and so Newton's third law says that you'll both experience the same force, just in opposite directions, and your acceleration is going to depend on your mass. So Tom and John are standing beside each other on ice. Tom has a mass of 60 kilograms. John has a mass of 40 kilograms. One pushes the other with a force of 360 newtons for 0.1 seconds. What is the acceleration of each? So this is the same idea as the previous question with the car and the mosquito. We are going to figure out what their accelerations are because we know that the force they're experiencing is the same. So let's do Tom on this side and John on this side. For Tom, we're going to do F net equals ma. We're going to use Newton's second law. And for John, we're going to do the same thing. F net equals ma, because we are trying to solve for their acceleration. Vector symbols. Okay, so they're both experiencing a force of 360 newtons, and we're given their masses as well. In this case, I'm going to rearrange things first to figure out the acceleration, but again, like you saw in the previous example, it's fine to put the numbers in first and then do the algebra, but I just prefer it this way. And so I'm going to divide by m to get the a by itself. Okay, but I also want to have my a on the left side. Doesn't really matter which way you put it. So a equals F net over m. And so our acceleration of Tom is going to be 360 newtons divided by his mass, which is 60 kilograms. And so Tom's acceleration is 360 divided by 60, which is just 6. 6 meters per second squared. Okay, let's say that Tom gets pushed toward the east. Okay, so his acceleration is going to be east. That's arbitrary. You could give it whatever direction you wanted to. It's just going to be a little bit easier to talk about John's direction if we have one for Tom. So we'll do the same thing here. We're solving for the acceleration, which is F net over m. Same thing, the acceleration is 360 newtons divided by, this time, 40 kilograms. And we get an acceleration then of 9 meters per second squared. And that acceleration is going to be the opposite direction, or west. So because John has less mass, he's going to have more acceleration. The lighter thing, the thing with less mass, is going to accelerate more than the heavier thing. Okay, now notice that we didn't use the 0.1 seconds at all. Not yet anyway. It's not necessary for figuring out the acceleration. We don't need a change in time in that formula. But in part B, we do need a change in time. So we're looking for what's the velocity of each of these after 0.1 seconds. Okay, so the 0.1 seconds is how long they're being pushed. It's how long it takes for the force to stop being applied. And so during that time, Tom and John are both going to be speeding up, and after 0.1 seconds they will have hit their maximum speed. So what we're looking for is V2, right? We know that both of their V1, their initial velocity, is 0 meters per second, and then when one of them pushes the other, they begin to accelerate for 0.1 seconds, and then at the end of that 0.1 seconds, they're going a new speed, a new velocity, and that is what we're looking for. So that's V2. So V2 equals what? That's what we're going for. Then let's list the other things we know, because this particular question is not necessarily straightforward for everybody. Sometimes it's hard to see what the path is to get from where you are to what the final answer is. And so making a list like this of what you're looking for and the things that you know is often helpful for making that a little bit simpler, a little bit clearer. We know that V1 equals 0 meters per second. We know the acceleration is 6 meters per second squared for Tom and 9 meters per second squared for John. We know the change in time is 0.1 seconds. And that's it. That's all we need. So when we look at the things when we look at the pieces that we're given and what we're looking for, they should often match an equation or a relationship that we have. You can reference your formula sheet, maybe you have it in your head. So in this case, this is the acceleration formula. Acceleration is v2 minus v1 divided by change in time. Now, it won't always fit perfectly into a formula just like that. Sometimes you'll have to take what you're given to find what we call an intermediate value so that you can use that intermediate value for your final formula. Okay? In this case, it's just straightforward. So let's first of all look at Tom. And we're doing acceleration equals v2 minus v1, which are vectors, divided by change in time. And same thing with John. John, his acceleration is v2 minus v1 divided by change in time. The only thing that's different between the two is their acceleration. So we are trying to solve for v2. Now v2 is shoved in the middle of this formula. I'm still going to rearrange the formula first, but as I often say, feel free to put the numbers in first if you want to, if that makes you feel more comfortable with the question. But it is good practice to rearrange it first. So I'm going to need to multiply by time because we've got a divided by time that's attached to both of these things. So multiplying by time is the first thing. Then I'll just have v2 minus v1 by itself over here. So I'll need to add v1 to the other side as well. And that will get me v2 by itself. And so my final version of this formula is v2 equals a change in t plus v1. You may notice on your formula sheet that we actually have this formula already written for you up there. It's just that we have it written v1 plus a change in t. Also works totally fine. So these are all vectors in here, just not time. We get the same thing over here. v2 equals a change in t. Those are multiplied together, plus v1. And then we can plug in our numbers. So v2 is this acceleration for Tom is 6 meters per second squared. The time he's experiencing that acceleration for is 0.1 seconds. And his initial velocity was 0. So this plus v1 part, that's actually not very important to have in here. So v2 equals 9 meters per second squared times 0.1 seconds plus 0 meters per second because John's initial velocity was also 0. And so we're just going to multiply 6 times 0.1 and 9 times 0.1. And so our v2, our final velocity for Tom, is 0.6 meters per second. And our final velocity for John is 0.9 meters per second. Okay, now we gave directions to the accelerations that they had in the previous part, and so we're going to just transfer those over here. Because their initial velocity was 0, their final velocity is just going to be the same as the direction of the initial velocity. So Tom ends up moving east, and John ends up moving west. If you have a good sense of what acceleration is, the change in velocity in a certain time, then possibly you could have done this question without this formula, right? Because in the end, all we did was the acceleration times the time. And acceleration times time will give you change in velocity. And because we knew that we were starting at 0 velocity, that meant that that change in time was actually the final velocity. And so there are other ways of solving these types of questions. You can reason through them in different ways, and they are also perfectly valid.